Okay, let's get started today. Alright, so we are plowing forward and learning on section 5.2 about the definite integral. Now, remember, surprise, we're not taking a test at the end of section 4, chapter 4. Great. Which meant it was kind of a little bit surprised. We just covered a little bit of material on whatever the last time that was, Friday or Thursday, I don't remember yet. And we are now trying to figure out a problem. A problem that's actually older than the problem Newton and Leibniz when they discovered the whole calculus thing. This is actually what they were trying to figure out how to do. They actually had to do the whole business of derivatives and stuff like that to figure this out. But this is actually kind of the opposite of derivatives. In fact, that's why in the end of chapter 4 we were talking about antiderivatives. Okay? But what the problem they were trying to figure out is trying to find some consistent way to figure out what was the area between some curve, a function that they were drawing, and the x-axis. Like in this case, they'd be trying to figure out this area. Between someplace over here, we'll call it A, and someplace B. What is this area? Now, you might think that that doesn't sound all that useful or helpful, but that's actually one of the biggest things in math. Okay, tons of real things in the real world are the area under a curve. We did an example last time we met where we talked about like, oh, let's just say this is the amount of heat coming from the sun at any given time of the day, and from this time to this time, the total amount of heat would be like the area under the curve, whereas like at any given time, let's just call that time t, this is the amount you're getting right now. But you add up this piece, this time, this time, this time, this time, and it adds up to the whole area under the curve. This idea of knowing about the area under a curve, between the curve and the x-axis, is like fundamental to physics, engineering, science, business, etc. So this is a big deal. Now, before we go back to what we were doing at the end of the last period, the book says, you know, we could sort of cheat if some of the functions that we were working with just made shapes. And you have a couple of problems like this on the homework set, where like they're saying, forget about goofy looking things that are, you know, sine of this plus cosine of this. What if the function that you were drawing, I don't know, let's say it looked like a, here's your function. It looks like a square. Okay? And you want to know what the area under the curve is, like this. Feel free to use 5th grade geometry. Okay? So, like for example, if this is A and this is B, and this value here is, let's just say, some constant C, well, the area of this rectangle here is just going to be B minus A times C, right? The width times the height. Feel free to do that, if it happens to just be a simple shape. And your book feels free to give you problems that involve all kinds of silliness. For example, what if your function looked like this? It makes a happy triangle. Okay? Where maybe this value right here is, let's just say H. Here's A, here's B. The area under this curve right here is just a triangle. 1/2 times the base is the distance from A to B, times the height. Feel free to do that if it's just a triangle. Okay? Or, your book has some problems where it's things like, it's a semicircle. This is the area you're trying to find. I mean, this has an equation. I don't know, I can't remember off the top of my head how to draw that equation. But if it's just a semicircle, and you know that it has a start here at A and an end at B over here, so this radius here is B minus A times 1/2. That's the radius of your circle. So let's see, pi r squared, so that thing's squared times pi, but then you have 1/2 of it because you only have a semicircle. Knock yourself out. That's easier than what we're about to do. So if you can just be cheating and say, you know what, this equation makes a graph that looks like a triangle, a rectangle, a square, a circle, things that are easy, not wiggly wow wow this mess, do it. Okay, that's not cheating, that's just being efficient with your time. B. An important point to understand about this is that it is the area between the curve and the x-axis. So like, for example, if then from your function, let's say after b, it continued and it did something like this from b to c, where now it's below the x-axis, that area below an x-axis is a negative area. So like if you had to integrate, if you had to figure out the total area under the curve, the equation will say, the problem will say, find the area under the curve, or whatever. You would figure this area here out, and that's the positive part, and this area that goes below the curve will be a negative, below the y-axis, that will be a negative area. Compute its area and then use that as the negative. Okay? So there's like the positive areas and there's the negative areas. Again, oh my gosh, this is huge. There's only about a zillion trillion applications of this.
Wait, couldn't you just do the same thing you would do from the top to the bottom?
Yeah, so like find this area, okay, so the width of this is going to be c minus b, and let's say this height here is, I don't know, let's just say h. Then this area here is c minus b times h, but then make it negative. Okay, because it's the area below the curve. When the curve is negative, when it's below the x-axis, okay? Alright, so if they're simple shapes, just do geometry to solve their problem. If they're below the x-axis, that part counts negative. If it's above the x-axis, that part counts positive. While we're thinking about it, before we go back to the evil of this situation of what if they're complicated, weird stuff. Once you start thinking about this as the area under a curve, certain ideas are going to start coming to your head. For example, I don't yet know how to do a shape that looks like this. But if I did, and I wanted to find this, so I'm finding this area under this wiggly thing, whatever it is, there's a couple of things I can definitely see are true. For example, I'm going to put another point in the middle here. Can we agree that the area of the whole thing is this area plus this area? So if we had some technique to find the area from like A to C, and we had some technique to find the area from C to B, we could just add this area to this area and get the area of the whole thing. You can add up the pieces. Does that make sense? There can be a bunch of those kind of rules. But we're going to start finding them. But before we do, we got to think back to what we were doing last time. Last time we said, hey, here's some function, f of x. I want to know the area between f of x and the x-axis between x equals a and x equals b. It's this area. The old problem. It's going to involve integrals. But we're not there yet. Well, we'll be there by the end of the day. But there have been ways in the past to do this. You won't believe them. For example, one way to do this would be to graph this on a piece of graph paper and cut the area out and just weigh the piece of paper. Okay? If you knew how much it weighed and you knew like 1 square inch of the paper weighs this much, can you see how that would work? Sometimes that's actually still done, well that's not done anymore with like computers and stuff like that, but certain types of integrals where there isn't a nifty math way that we're about to do, they still did that until fairly recently. Like students would do that as an activity. They cut the area out and they weigh it, and then they know, okay, 1 square inch of the paper weighs this much, so how many square inches did you have? Pretty neat. But that's kind of only as an idea what we did the other day. The other day, what we did is we divided this up into little pieces. These little rectangles. And we said, let's make n little rectangles. Each of those n little rectangles has some width. They are, what was it? B minus a divided by n wide. Right, the distance between here and here, divided up into n little pieces. And each of these little rectangles had some height. It was f of a plus I minus 1 times, we'll call it delta x, the width of each of these little guys right here. In fact, why don't we do that over here then too? We'll call that delta x as well. Where this is, that I is like, this is 1, this is 2, this is 3, this is 4, and we're just adding up all those little rectangles. That's actually a perfectly valid way to do this. It's obviously not perfect in the terms, like this little rectangle here has a little extra piece here, and this one has a little extra piece here, and this has a little extra piece here, and this has a little extra piece here, but like these rectangles are a little bit short. And it can be shown that overall this works pretty good. But you know how it's going to work better and better and better? Make n bigger and bigger and bigger. Divide that little area under the curve up into smaller and smaller, well, skinnier and skinnier rectangles. And we did this the other day. We talked about how, in fact, if you could head towards having an infinite number of those little rectangles, where you add up from 1 to n, like how many little rectangles, each of which is delta x wide, and f of a plus I minus 1 times delta x, where that is there, or there, or there, you would have a damn good approximation to that area. It approximates that area there. The good news is, math gives us a tool to do this without going through all these limits and at infinite sums. It gives us the definite integral. Now remember, back at the very, very end of chapter 4, we did indefinite integrals, which was basically the same thing as just saying antiderivatives. In fact, it was just a notation difference. Remember, like if you had f of x was x squared, we found the antiderivative of that, or the indefinite integral of this, by increasing the power by 1, so it's x cubed, and we took this number out in front and changed it to 1 over that. And then we had to add that c at the end. Now, you had a whole bunch of practice with these things, and they were kind of fun. And we're going to have lots more practice today and moving forward. That was the indefinite integral. Indefinite integrals have that plus c indefinite integrals. Remember, this is the beginning, this is the end of it, like this is like the notation or whatever, everything in between is what you're integrating. It's an indefinite integral because there isn't a number here and there isn't a number here, and when you're done you have to have that plus c. Do you remember what that means? The indefinite integral means this thing's derivative is this thing. But here's the deal, this is also the same thing as the area under the curve if we do the definite integral. Allow me to show you what's about to happen with a definite integral. The definite integral. The definite integral will be the area under the curve between a and b. Between some number a and some number b. Then we're going to write it as the integral from a to b of our function dx. This is just a notation thing here. Remember, this is like how we know this is the beginning. Like, what are we taking the integral of? This thing. The thing between the integral symbol and the dx. The dx is telling us that we're integrating on with respect to x. I don't think anything in our class is going to get as far as like where there's y's and z's and all that crap in there. But if there ever did, we'd have to have that there too.
So what you're saying is if you took a function, found the derivative of it, the original function would be the equation to find the area of the derivative of the function.
No. The integral of the function will be the area.
Right, but so it'd be the antiderivative.
The antiderivative. I think what you said would have been true if you said
So,
antiderivative.
If you found, there's like the function,
Yes.
you found the derivative.
Uh-huh.
This would be the equation to find the area.
Probably, yes, I think that's right. In fact, I think what you're saying is section 6.3 or 5.3, whatever chapter we're in, the fundamental theorem of calculus. How derivatives and integrals are like opposite. Derivatives and integrals are like plus and minus, or multiply and divide. They're like inverses of each other. Okay? Or log and exponent. Okay? Yes. But we're not going to go there till like later this week.
Okay.
Okay. The answer to this problem will be that antiderivative. I'm going to go back and use that big F. It is the antiderivative of this, except instead of being at x, it's at b, minus the antiderivative of this at a. Let's do one. It's kind of like when we were doing derivatives. Once you got the pattern, dare I say it, was almost fun. Let's do one of these guys.
Wait, this sounds like it'd be easier than indefinite integrals.
Yes, in some ways, yep.
Then why would we do...
I don't know. Every textbook out there does it the same damn way. I don't understand. All right, so let's do this. Let's do the integral from 0 to 5 of x squared dx. Just so you understand what's going on here, what we mean, the graph of x squared looks something like this. So from x equals 0 to x equals 5, I want to know what this area underneath this curve is. Between the curve, f of x is equal to x squared and the x-axis. All we do is compute the antiderivative of x squared. Okay, remember how we do it? If it's a power rule, all we do is increase the exponent by 1, and out in front we have a coefficient where it's that new 1 over that new exponent. So here's our antiderivative of that. But it's not a... Okay, so that's the antiderivative. Let's write it that way. So that's the antiderivative. But we need that at b minus that same function at a. So that function at b in this case was 5, minus that function at a, which in this case was 0. 125 thirds. Hey, I'm going to have a better way to write this in just a little bit. But just to be clear, it's just that little tiny step. This is this area. I'm going to give you a better way to write this. We wrote this, the integral from 0 to 5 of x squared dx. The antiderivative of the x squared was 1/3 x cubed. We need to evaluate that at b and at a. The notation for doing that is a line with a and b's value at the top and bottom. That notation means plug this top thing in, minus, plug that bottom thing in. it's this line, it's usually, I kind of got out of control here, but whatever, that says, it shows you the limits of the integration, where are the endpoints. Let's do another one. I got a simple one. How about my function f of x equals x? No, how about x plus 3? So if I made my graph here, the y-intercept of that function is at 3, the slope is 1, it's something like this. And let's do the integral from 1 to 4. So we're talking about the area of this trapezoid right here. The area under that curve, a curve in this case a straight line, but whatever, from 1 to 4. Could you do this with geometry? Oh, I suppose you could. What? The height times the average of the bases kind of thing, whatever. You could do it. You certainly had times in your past where you could do it. But let's do it this way. The integral from 1 to 4, we're integrating the function x plus 3 dx. If it makes you happier, put parentheses around this. It makes me happier, but it doesn't necessarily, the book goes back and forth as to whether it cares or not. Alright, so we need this integral. Well, okay, to do this, we need the antiderivative of x plus 3. Alright, remember, that is, the antiderivative is, we can take the antiderivative of this, and then we add the antiderivative of this. What is the antiderivative of x? We increase the power by 1, and we multiply by that new exponent, we take 1 over that. So the antiderivative of x is 1/2 x squared. What's the antiderivative of 3? Remember, 3 is the same thing as 3 times x to the 0 power. So that's going to be 3 times x to the first power, 1 over that power. Well, that's a fancy just way of saying 1. And x to the first power is just a fancy way of saying x. So this is the antiderivative right here. And we're going to evaluate that from 1 to 4. That means plug in 4 to this thing. 1/2 4 squared plus 3 times 4 minus, now plug 1 into that thing. 1/2 1 squared plus 3 times 1. Let's see. 8 plus, this is 20 minus 1/2 plus 3. 1/2 plus 3, 6, that's 7 halves, 20 minus 7 halves, 40 halves, 33 halves. Does that sound right? I think I did the arithmetic there, right? So this area here was 33 halves. It is the distance from here to, well, the integral of this function from 1 to 4. We took the antiderivative of the function and we plugged in the values at the ending of here and the beginning of here. This works for all the different functions that we even had examples of back in 4.10 or whatever the last section was where we did antiderivatives. How about the integral of cosine of x dx from 0 to 2 pi.
Aren't you going to draw it?
Oh, maybe. Hold on for a second real quick here. I want to double check that I have the same thing as what they do on this. Hold on. We need to know the antiderivative of cosine. Well, I'm looking something up. Hold on. What is the... We had this back in... What was the antiderivative of cosine? Do you ever remember? Sine. Yep. So the antiderivative of this is sine of x. Remember how we know that? Because this thing's derivative is this one. Fundamental calculus keeps sneaking up on us. So sine of x is the antiderivative, but we needed to evaluate that at 0 and 2 pi. Alright, so that's the sine of 2 pi minus the sine of 0. Right? We plug in this one, we plug in the minus, we plug in the other one. Let's see, what is the sine of 2 pi? Oh, it's 0. What is the sine of 0? Oh crap, it's 0. 0 minus 0 is 0. Oh no, that can't be right. Things must have gone horribly wrong. Why would the area under the curve be 0? What is this curve again? Let's see. It's the graph of cosine. Let's see, cosine starts up here at 1. At pi over 2 it crosses. At pi it goes down here. Up here to 3 pi over 2, it's over here. Up to 2 pi, it's right here. So hey, wait a minute. Is it starting to be clear why this integral was 0? Because we had some positive area, we had some negative area, and we had some positive area. And when we integrated over that whole thing, we got 0. Shall we check if this makes sense? I think we shall. What if we are understanding this correctly, then shouldn't the integral from x equals 0 to x equals pi over 2, that should be a positive number, right? Let's see if that works out. If the integral from 0 to pi over 2 of the cosine of x equals as dx, is that going to be a positive number? Let's find out. The antiderivative of cosine is sine, and we're evaluating this from 0 to pi over 2. That means that it's sine of the top number minus the sine of the bottom number. Sine of pi over 2 is 1. Sine of 0 is 0 equals 1. This area right here happens to be 1. Hey, if we're doing this right, it seems to me like this area should be negative. The integral of cosine from pi over 2 to 3 pi over 2 should be a negative number. Let's try that. So is the integral from pi over 2 to 3 pi over 2, is this going to be negative? Let's find out. So this is the antiderivative is sine, and we're evaluating that at the beginning and the end. So it's the sine of 3 pi over 2 minus the sine of pi over 2. Let's see, the sine of pi over 2 is negative 1 minus the sine of pi over 2 is 1. Negative 1 minus 1 is negative 2. So the area of this little piece here is negative 2. Which actually kind of makes sense, right? If this little chunk here was 1, can you see, like, flip? It should be negative 2. Oh, these are fun! They have all kinds of nifty properties which are summarized in a table in your book, properties of the definite integral. All kinds of fun things. For example, any kind of integral of, like, I'll just use a number, 7 times f of x dx. So anytime you have some kind of constant, you know, like maybe this is 7x squared or something, you can always pull the constant out in front and then just evaluate the integral of the piece that's left. That's okay. Right? So like, for example, if our integral was 7x squared dx, that's the same as 7, here let's actually put some limits on here, how about 0 to 1? That's the integral of 7 times the integral from 0 to 1 of the x dx. 7 times, let's see, what's the antiderivative of this?
1/2 x squared.
No, 1/3. You increase the power of this by 1, and then out in front of it, you make a coefficient that's 1 over that power.
Right.
Yep. And then that's going to be evaluated from 0 to 1. So this is 7 times 1/3 times 1 cubed minus 1/3 times 0 cubed. So this is 7/3. So many interesting problems begin to be able to be solved with this. I'm so happy. All right. But you need some practice.
No.
Yes, you do.
No. I think we got it.
You got it. I'm going to take your word for it. Oh, man. Okay, what do we got here? Plan for trig, that's out of here. All right. Matt thinks I was born yesterday.
Sake of that.
All right.
I'm just saying, yesterday was a pretty nice day, so what's wrong with that?
Yesterday? In the driving rain?
Yeah.
You need practice on these guys. You know what? I'm just going to unplug this and unplug this. And I'm going to give you page 544. It's number 71, 73, 75, 89 through 93 odd, 99 through 103 odd,
Oh my gosh.
111 through 115 odd.
Oh my.
You need practice. And 141. You got nothing else going on.
I got a paper for us for tomorrow.
Do you? What's it about?
It's a persuasive paper.
What are you persuading?
Second Amendment, and its relation to pretty much everything.
Okay. And how long is this paper?
Huh?
And how long is this paper?
It's a speech.
Yeah.
Oh, it's a speech.
I'm writing it. Paper.